Alrighty, so we are up on YouTube and folks are still pouring in, but we'll start off by saying welcome. And for anyone who's joining us on Zoom, the usual warning, which I can't imagine anybody is sick of yet, which is that if you want to chat with others in Zoom, then please make sure that your little bar in the chat window is switched to all panelists and attendees, not just panelists. Otherwise, you'll just be talking to us three, which we're happy to have, but it'd be nice for you to talk to everybody as well. And feel free to let us know where you're from and how the weather is doing there. Here in Toronto, it is pretty mediocre, but at least it's warm. So, and today we have a very exciting show for you today because we are joined by Alan Dyer, who is a long-time RASC member and also phenomenal astrophotographer out in Alberta, and has some amazing tips, tricks, knowledge to share with us about the Aurora Borealis, which is one of the main things that he photographs. I also wanted to quickly mention as well that it is officially 1 year since we started this show. Happy birthday to us. Yay! It's a bittersweet celebration because it's been fantastic to get to know everybody who's joining us on these live streams, and it's been great to be able to provide you all with this live stream and with all this like extra space content. But it's hard to believe it's been a whole year since we stopped seeing people in person. So
true.
We hope to be able to see you all in person soon. And until then, we'll just keep on talking about space on the internet. Yeah. I'm gonna hand things over to Chris.
Yeah, hi everybody. So the reason that we picked today for talking about the Aurora Borealis is because the times of the year around the equinoxes are among the best times to see it. And I'll get into a little bit about why that is in a couple of minutes. I'm going to put my geophysicist hat on and talk a little bit about the Earth's magnetic field to start us off. And I'll just share my screen so we can see some diagrams here. And we'll do that. So lots of people have seen this sort of a picture before. It's showing the magnetic dipole-shaped magnetic field that originates in the Earth's core. And what you might not think of, but which is sort of obvious when you think about it, is that magnetic field actually is inside the Earth, at the surface where we live, and it extends into space. And so we're actually living within a magnetic field that's all around it. It permeates everything. And when you pick up your friendly compass, you're actually detecting the direction of the Earth's magnetic field. Now, a magnetic field or any field has an intensity or a strength and a direction. And that's why you see all these little arrows and curves and things like this. And essentially what's going on is that the magnetic field lines are exiting at the south magnetic pole of the Earth, looping around and re-entering at the north magnetic pole of the Earth. And the magnetic pole is not coincident with the axis of rotation. So the North Pole, which there might be, well, there's certainly at the South Pole, there's a post with a chrome ball on it that marks the South Pole of Earth's rotation axis. That's not where the magnetic field is. In fact, if I bring up this map of the Earth's magnetic field, this is a cool little tool that you can get in online. It's at the NGDC of NOAA, or the National Oceanographic Atmospheric Association. I can't remember all the acronyms. But what's neat is that these contour lines are the strength of the Earth's magnetic field. So in a place like Canada, the Earth's magnetic field has a given strength, and it basically aims north, but it's not just aiming north, it's also dipping downward. So if you go back to that other picture for a second, you can see that the magnetic field lines dive into the Earth. And so when you're using a compass, you're only picking up one vector of that field. If your compass was a three-dimensional compass, it would actually tilt a little bit downward. And the farther you get to the Earth's north magnetic pole, the more vertical it would get. And you may have seen movies and things where people have a compass at the north magnetic pole and it's spinning. And that's because the field is not really horizontal there, it's vertical down. And so you really need your compass to be sort of sideways and pointing down. And that magnetic field north magnetic pole actually moves underneath the Earth's crust because it's the Earth's core that's doing all the action here. And this little tool will let me actually plot the diagram of where the Earth's magnetic pole has been. So Canada currently owns the magnetic pole. That hasn't always been the case. You can see that it was back over in Siberia for a while. And then around the early 2000s, it's been around here. Let's see if I have the direction. Yeah, so at the present time, it's actually drifting out of Canada more towards the true axis of rotation of the Earth. So that's a neat little tool that you can log into and play with. I think Jenna could share the link for that one. Now, if the Earth was sitting by itself in space, then the Earth's magnetic field would be nice and symmetrical, the way this diagram is showing it. But that's not true, because we have another source of magnetic fields stronger than ours next door to us, and that's the sun. And so what the sun does is its magnetic field pushes out into the solar system, and it pushes on Earth's field, it pushes on Jupiter's field and Saturn's field, it extends well into the solar system. And the couple of things that happen because of that is that we get a pressure on the sun-facing side of our magnetic field that squeezes it in and flattens it, as you can see in this diagram. And then on the back side of Earth, the trailing side, we get a long tail that stretches out, and it's called the magnetotail. The whole thing, this whole funny shape, this teardrop shape, is called the magnetosphere of the Earth. Now, I'm not going to go into loads of detail here, but basically what happens is when the charged energy, the particles from the sun arrive, rather than just land on Earth, they get deflected and pushed off by our protected magnetic field, and they actually get deflected north and south. And so you can see that there's kind of a cone here where the magnetic field lines diverge from the north and south magnetic poles of the Earth. And the solar particles actually get diverted north and south and dive down towards the Earth. And that's what causes the aurora. The aurora happens when the particles from the sun encounter the atoms of our atmosphere. And for that to happen, those particles need to get close enough to the Earth to get within 100 or a few hundred kilometers of the Earth's surface in order to start contacting with the oxygen and nitrogen and the other atoms in our atmosphere. And so you get aurora happening preferentially around the north magnetic pole, but also in the south. So we have the aurora borealis, which borealis means north. We have the aurora australis, which means south. So I follow a gentleman from New Zealand. He's constantly posting fantastic pictures of the aurora, just like we have our Alan Dyer here. They have Ian down there, and does the same thing. And basically, when the aurora kicks up, for us, it's kicking up globally. So the southern hemisphere is getting the same sort of kick. Let's see if there's anything else I want to say before we just open it up here. Yeah, let's talk about the ring. So you can see behind Alan's picture, he's got a green glow behind him. And that's the aurora, the auroral oval. So let me just open up the auroral oval here. Let's see if I have that one open up. Let's see, here we go. So this green glow is actually the sort of steady glow of the aurora that's happening kind of all the time in a low simmer. And when the sun sends us a stronger blast, it fires up our magnetic field and it causes that energy gets dumped into the north and south pole, and that ring expands, and as it expands, it moves south. And that's why we only occasionally see the aurora at southern hemispheres. This is the animation that you can play with on this website. If I can get this to play, it's loading up. And you'll see how, as the Earth rotates, the ring moves around. So here we go. So you can see the bright half of the Earth is the sun-facing side, and the dark half would be the sun-away side. And so just because you get an alert that the aurora is coming or it's happening, it may not be working for you because it may be on a part of the world that's where the ring is more intense right now, and it may not be intense where you are at that particular time. I'll stop there. Alan, what do you want to contribute here?
Yeah, that was great, Chris. And just to be clear, because something that people often hear about, and there's often news items that pop up every now and then, that somehow we're losing the aurora. Because as you showed on your map there, the North Magnetic Pole is moving away and moving north quite rapidly right now. And that is indeed where your compass points to. And people are then sometimes afraid, and sometimes the news reports, in fact, declare that somehow the aurora is moving away from us, like moving away from us in Canada. We're not going to see them anymore. That's not true.
No.
There's two magnetic poles to be confused, even more confusing. There's two magnetic poles up north, the North Magnetic Pole, which is where your compass points to. And when you're at that pole, it points down. As you said, magnetic dip is downwards, but there's a North Geomagnetic Pole. And that's where the aurora particles are trying to get to. And that's what's at the center of that oval that you're showing there now. It's the North Geomagnetic Pole. And so that's the area where the aurora particles are trying to stream down in that conical pattern that you showed in the diagram. And that hasn't moved much in decades and isn't moving much. So don't be afraid that somehow, oh, I got to see the auroras in the next couple of years because they're all going away. They're not. For example, up in Churchill, Manitoba, where I up until a year ago was leading tour groups every year in the wintertime. There was a rocket range built there in the 50s and 60s. And it continued in operation through the 70s to fire rockets up into the aurora, which was happening straight overhead because Churchill is underneath that oval. As you can see, when the little animation comes around, Churchill on the west side of Hudson's Bay is underneath that normal position of the oval. It still is. And the rocket range is shut down, but you could still do research there. And, the aurora, like it is right now in your animation, is coming right over that. It still does, even, 50 years after the rocket range was built for the geophysical year in 57. So,
but we can lose the aurora due to light pollution, though, right? In a sense.
Well, people that live in cities certainly do lose the aurora because of light pollution. And so anybody, and I often hear this, is where, oh, I remember as a kid seeing the aurora so often, and I don't see it anymore, thinking it's gone away. No, the lights have hidden it. It's still happening just as frequently. With an 11-year cycle, we can talk about that, which is now on the upswing again. And so the aurora does go up and down with the sunspots and solar activity. But aurora is happening just as frequently as it was decades ago, and is just as visible. It's just that you live in more brightly lit cities than you did whenever, depending on your age, when you grew up as a child, and so you're just not able to see them as frequently. They can be seen in the city if you get a really bright display, but typically you got to go out into the country to have any chance of seeing an aurora borealis display.
Yeah. So I brought this website up here because it's got the we have spacecraft that are in orbit that are positioned in the solar system to keep their eye on the sun. In fact, we had a pair called Stereo A and Stereo B that were positioned to be able to watch the backside of the sun that we couldn't see from Earth, to warn us when some of the magnetic activity regions of the sun were getting ready to turn and face us. We lost one of the spacecraft a couple of years ago, and we didn't lose it, but it stopped sending its data here. We may reestablish contact at some point. But if you're interested in what the sun's looking like at any given time, you can go to the Space Weather Live.com gallery, or you can go to the various solar dynamics observatory images and things like that. This one here, I could just make a little bit bigger. So what you're seeing here is a magnetogram. So basically the greens and the yellows would be where the magnetic field of the sun is poking up or sticking into the sun in a polarized fashion. It's these magnetically active regions that are, to worry about in terms of sending blasts our way.
Yeah, the sun is a bit quiet right now, I think, but even well, about a week or days ago, or right around the equinox, at 20th or 21st, we had some great displays. It didn't really get bright till about 2 or 3 a.m., but the diehards were out there and got some fabulous shots. We've had some good displays, and as you said at the top, it's around the equinoxes, September and March, when the sun's magnetic field and the Earth's magnetic field seems to connect the best, and we get the best displays. We can get displays anytime during the year, not just in the winter and not just at equinoxes. I've seen great displays in midsummer, especially from Western Canada, southern Western Canada here, where it's dark enough in summer, even in June, to see the northern lights, but we can still see them, whereas further north, up in the main auroral oval area, up in Yellowknife and up in the Arctic, it would be too bright, so they don't see auroras, even though they're happening. They don't see them in summertime. Their aurora season, places like Yellowknife and Churchill, does go from late August or September through to March or April. It's just kind of ending now in, say, Churchill or Yellowknife, aurora viewing and tourist season, when the tourists are able to go back there again. And so, but the aurora is happening year round. They're not a wintertime cold phenomena. The aurora doesn't care how cold it is down here. It's happening way up there, and it can happen all year long. Long winter nights, you might have a better chance of seeing them in the summertime, but I've seen great displays right at summer solstice from here, southern Alberta. Western Canada, we can get them year long, visibly obvious year long, around all through the year.
Well, that dipole magnet diagram of the Earth that I showed, I mean, the sun has a similar one, and of course, magnets that are aligned in the same direction repel one another, and so that helps to fend off the charges from the sun's particles that are coming in. But at the equinoxes, the Earth's magnetic field, the Earth's axis is tilted neither toward nor away from the sun, but kind of sideways to the sun, and so there's less of that north vector that matches the sun's north vector. It's weaker, and so that kind of lets the particles through a little bit more easily at those equinox in March and September every year. This animation that I'm showing you here is a little bit busy, but I wanted to express the concept that when you get an alert on your phone that Aurora, to be on the lookout for Aurora, it's because the particles that are coming to energize the Aurora take a couple of days to get here from the sun. I mean, they're not light rays, they're actually material that's journeying out into the solar system. And as the sun rotates and it puts out these blasts, you can see this sort of these colored arcs rotating around as the sun rotates on its axis. And it blasts one of these jets out, and it, of course, moves like ripples in a pond, where it gets wider as it moves away from the sun. And so if the Earth is on sort of the same side of the solar system as that blast, then we can expect to receive the energy. But if it turns out that it sends the blast on the opposite direction, then the Earth may get missed altogether and we don't get anything. So that's why, their predictions aren't exactly, they're like weather. I mean, they're a chance of, but they're not 100% guaranteed.
Yeah, if you go to websites, I think we're going to bring up some of the apps or whatever, or a website that's popular and viewers may know about it, spaceweather.com. Yeah. You'll see information about that yes, these satellites have observed an eruption on the sun, something's coming our way, and expected in a couple of days' time, or it could be arriving tonight or whatever. That's a forecast, and it's still iffy, because one of the things you talked about, Chris, is the direction of the magnetic fields of coming from the sun versus the Earth. And to really connect and make a good display, the sun's magnetic field, or the interplanetary field, has to be pointed south, and our field in the Earth is pointed north, and opposites attract. And so we need, and it's called the BZ index.
Yeah,
the
so that's here at
direction.
If you go to the spaceweather.com and scroll down a bit, you can see those numbers.
You'll see it right there, right there, BZ -2 right now, if that's your live. And so we like that to be south. And so you can still get the potential of this solar storm hitting the Earth and disrupting our magnetic field. But if that magnetic field from the sun is north, it may not connect, and we get a dud. Essentially, nothing happens. Nothing much happens, except way to the north, you might get a good display regardless. But for us down south here, expecting a great display, suddenly it fizzles, because that magnetic field just doesn't go south. We want it to go south. The BZ, and it can change in literally a few minutes, north and south. So suddenly, where there was no aurora, it can change and go south, and then we get suddenly the aurora really brightens and puts on a good show. But
So let's tell everybody about the KP index.
Well, that's the other number we watch, and that your Aurora apps are going to be, you even set your Aurora app to go off with a notification if a KP goes above 4 or 5, which is kind of in southern Canada, northern.
Yeah.
But the KP is just from a German word for number, and it's just planetary index. It goes from 0 to 9. Scale, and we just like it to be as high as possible. Typically it's 0 to 1 to 2, and that's producing standard run-of-the-mill displays of aurora from underneath that auroral oval up in the Arctic and Northwest Territories, and putting on a good show regardless. But when it gets above 4 or 5, that's when you can see have a chance of seeing something more in the way of a display from, say, southern western Canada here, Winnipeg KP3 or 4, Alberta, where I am, a little towards the west, KP4 to 5, southern BC got to be 5 to 6, and southern Ontario 5 to 6, and if it's going up to KP8 or 9, which it might do once or twice a solar cycle, or rarely, that's when the aurora can appear down from the southern United States. Even it's a rare night, but that's infrequent. But typically, people start to get excited, and that auroral oval lights up red, like literally they color code it red if it gets above KP4 or 5, and that's when you have a chance of seeing something from across Canada, particularly Western Canada. We have a better chance here than southern Canada, which is farther south and farther east away from that oval.
There's a question from Al about the BZ index. Is it an index? The why it shifts, why it oscillates from north to south.
Oh, that magnetic stream of material coming from the sun got magnetic fields embedded in it from the sun, and it's wobbling up and down in direction quite a bit, as Chris showed in that kind of rotating lawn sprinkler kind of image. You can sweep through areas of the interplanetary field that's going up and down in direction in the space of a few minutes. And so that material coming from the sun is very messy and chaotic.
Yeah.
And so that's why it can be, you can only make a prediction that you have a chance of seeing some aurora tonight. There's never any guarantees. So people look at the KP index, but it's also the BZ or BZ, depending where you are, that people are watching in Aurora apps literally minute by minute to say, hey, it's turning south. And even then, it might take a little while before that material gets to us and actually lights up the aurora and causes a bit of a substorm to appear in our sky.
And I guess that has to do with like the turbulence inside the sun in terms of its own magnetic field?
No, I don't think so.
Well, they're all different. They're all different regions on the sun that are emitting at different times, and so we end up experiencing the sum total of all of those. So it's almost like a breezy day where you get a gust of wind and then a quiet and then a gust.
Yeah.
When I used to do geophysical prospecting with a magnetometer, we would be recording. We'd take a reading every couple of minutes or every half a minute. But we would have a base station running the whole time, watching the base field at the base camp. And later on, we'd have to subtract the variations we saw on the base station to make our readings steady, to make a map out of it. Yeah, so it varies on on minutes, easily seconds and minutes.
It's a very messy process. It's never as simple as it depicted in the diagrams that we inevitably kind of show when we explain this kind of material. It's really fluid dynamics. If you watch sort of computer simulations of what's going on in the magnetic field, there's all kinds of complex turbulence going on minute by minute and on a very small scale and large scale structures, and so it's very messy to even simulate, let alone predict exactly what's going to happen in the Earth's magnetic field and its interaction, that interface between the stuff coming from the sun and that deflector shield that's around the planet at all times.
Yeah, the other thing is, don't strictly depend on the app. If you're out stargazing and you look to the north and you see a glow in the sky and you think, that's not a cloud bank, is it? It may very well be an aurora that you're picking up. The trick there, of course, is to snap a photo if you can, a bit of a longer exposure to see if you can pick up the characteristic green glow.
Yeah, that's when there's what I do. I live out in the country, and it's often what I do if there's prediction for an aurora that night. I'll take a camera, and one of the cameras I have, the Sony, is so good in live view, it actually shows the aurora live. And what to the eye just appears, is that aurora? Or, it's still faint, it hasn't gotten bright yet. Is that aurora, or is that just cloud or light pollution of cloud or whatever? And then I'd take a shot or actually go to live view on the camera. Oh, there's green. There's a green arc there. Yeah. It's aurora. Now, is it going to get bright enough to get excited about? But yeah, that's something you can do. And we can get into photography as well, but even people with today's modern phone cameras can get pretty decent shots of the northern lights as well.
Let me bring up your website and we can start talking about the different kinds of aurora, and you can comment a little bit about how to capture them.
I'm gonna also just jump to a question that was just asked by Paramjot in the chat, which is it always green? And that will be answered very shortly by just looking at your photos as well.
Yeah, I mean, I have some notes about that, which we can get into here. I'll just summarize quickly what's going on there. The green color is being pretty, here, let me actually bring you a diagram up. This is a diagram of an auroral. Open this up. So when the energy from the sun hits the atoms of the Earth's atmosphere, it knocks the electrons away from the atoms, and when they fall back into place, they emit photons of a particular color of light. And you can see here that the oxygen atoms will emit a green light at a singular or singularly ionized level, and then at higher ionizations, they'll give off red light at higher angstroms. And so you can get the green primarily from the oxygen, some red from the oxygen. You can also get some blues from the nitrogen and some of the other colors. And also the concentration of the atoms in the atmosphere, the density of the air dictates how much light you get and how much ionization you get as well. So for example, the greens happen about 100 kilometers above the ground, 100 to 300 kilometers. And that's why you get the curtain effect, because below that point, you're not getting the effect happening anymore. The blues and pinks come from the nitrogen. They're about 100 kilometers up. And then the reds would be even more strongly ionized. They tend to be higher above the Earth's surface. And and Alan, feel free to pop in with anything further.
If you see any, well, your camera detects the color very easily, almost all the time, green. But the aurora has to get bright enough to excite the color receptors in your eye so that you see green with the eye. But the green is the most prominent because as you see here in your spectra, it's the most brightest, the strongest emission line from oxygen. And it's oxygen and nitrogen that are primarily producing the colors, because that's what our atmosphere is mostly made out of. But it's the oxygen that's producing the majority of the colors. The green is by far the most common. That's what you see all the time. The red, as you see to the right of your chart there, it takes a much more higher energy aurora, and that red color is usually at the top of the curtains. And your cameras can pick that up, but it's rare for your eye to get see that red. It takes a really intense aurora, and I've seen it where the sky is literally blood red over the whole sky, and you know, historically that's what people used to see, or did see historically, and reported, you know, these blood red displays in the sky, and a sign, an ominous sign of something nasty about to happen. And so you can get red to the eye, but that takes a very, you know, KP 6, 7, 8, 9 kind of display for that red color, because your eye is not sensitive to red. That's why we use red lights, you know, in our observing, you know, to protect our dark adaptation. But your eye is more sensitive to green, so it can see it more easily. But it can happen where you see reds. The other colors that you do see from time to time when the display gets bright enough is, as you said, that pink. It's a fringe of pink along the bottom edge of the along the bottom edge of the curtain. And that pink comes from nitrogen. And it's a blend of, I'm not sure if you go to Aurora gallery there, Chris. Not sure, and under Yellowknife there might be some shots of the pink fringe, but that's a mixture of red and blue coming from nitrogen. And let's see if we can find one or two. Well, I'll just scroll down. Just there might be some there in yellow. These are shots from Yellowknife from last time I was there in 2019.
Just amazing.
And you can see some purples there as well. And so that's from oxygen blending with some nitrogen, maybe even some hydrogen sometimes can add some colors. But typically to the eye, you can see some pink fringe along the bottom of the curtains, and that's nitrogen glowing. And that looks really pretty. And you do see that with your eye at times when the aurora gets quite bright, and not just from Yellowknife, from anywhere when the aurora gets bright. So the green and the pink, it's the pink that I always say to people, you know, in my tour groups, look out for that. They can see a little bit on the left there where your cursor is there. Yeah, right there is a little bit of
fringe,
a little bit of pink. But you can see some of the colors there that the camera picks up, but that your eye will when the aurora gets bright, and you have a better chance of seeing a bright aurora if you chase up to a more northern latitude that rather than wait for it to come to you.
I'm going to steal the sharing to just quickly, it's this little pink bit here that you're looking for, right?
Yeah. Oh, there we go. There. That's a good example from Churchill. Exactly. And that's what you would have seen with the eye when it gets that bright. That is what it does look like with the eye. And what a still picture like this can't capture, but if you search on the internet, you'll find videos, not time lapses, but real-time videos, because the cameras are good enough now to do it, capture in movies in real time. You see that pink rippling along, just chasing along. And wow, that's what people pays their money to see. And it's pretty amazing. It's the motion, which can get very rapid when the display gets bright. It's not only the brightness, it's the motion that really picks up in intensity. When a substorm comes in, you get the electrons are raining down with greater frequency or greater intensity. These are all from Churchill.
And these look like they were almost taken in a series where you could sort of see some movement, eh?
Yes. I've got a YouTube channel and a Vimeo channel. Amazing. Just search for Amazing Sky on YouTube or Vimeo, and you'll see not the most recent videos, but you look in the back catalog, you'll see some music videos I produced with time lapses and also real-time videos from Churchill and Yellowknife, where you'll see the motion and the colors and whatnot as well. So it's very impressive. I don't know how many times I've seen displays and you don't tire of it. It's jaw-dropping always when you get a great display going. And I was hoping to get up to Yellowknife last September. That was kiboshed, and maybe this September. These are shots from my last trip to Yellowknife in September, which is a great time to go to Yellowknife because it's not in the middle of winter. It's dark enough to get displays showing up. It's just starting aurora season. So lakes like Prelude Lake there you see, and the water, Rampart waterfalls, it's still open water. It's not frozen yet. And you get great displays. So it's a wonderful time to go up to Yellowknife in the first 2 weeks of September or so. I've been up there a couple of times now, and at that time, and hoping to get back this year.
On that note, we have a couple questions about tourism.
Yep.
Do you want to talk about Aurora tourism quickly?
Sure, it's huge, or was.
Yeah, not so much anymore, maybe.
Yeah, places like Yellowknife and Churchill, which depend upon the Aurora tourism, it's a major part of their economy. Up in Yellowknife, there's big hotels that we're expanding and constructing to accommodate the influx of tourists until the last year. But that'll pick up again. It's huge. I lead tour groups in Churchill. There's some shots from Churchill at a place called the Churchill Northern Studies Center, which is a research center for scientists to go and use labs and study all kinds of aspects of Arctic and boreal forest ecology, but they don't do aurora research as such, but they host tourist groups for the polar bears in October and the belugas in June, and then the auroras in February and March. So Ron Waldron, RASC member from Saskatoon, and myself, we switch off different times, different weeks, and usually there in February and March, we go to Churchill to lead tour groups. And then Ron and I both lead groups in Norway, or were until last year, on a cruise ships up and down the Norway coast. And so places like that really attract a lot of aurora tourists. Iceland, I've not been to, but that's another popular spot. And again, you say Yellowknife, Whitehorse, and of course, Alaska, huge Fairbanks, kind of again, one right underneath your auroral oval. So that's usually popular for any from the US because you're just staying in your country, up to Alaska. And so it's huge with people from around the world coming to these aurora cities and locations in Scandinavia, Iceland, Northern Canada, Alaska, to see the Northern Lights as part of a several night trip, which includes dog sledding and whatever it is that they also do. And these are not amateur astronomers. These are people that it's their bucket list. That's what we hear all the time. I want to check it off my bucket list to see the Northern Lights. And typically, certainly in Churchill, we always deliver. There's only been one or two groups that have not had clear skies and not had auroras over the decades that they've been doing tours. So typically, we're able to deliver, and people go away happy. These are some shots from last year's trip, which was 2018, a couple of years ago.
So what's the minimum length of time you'd want to be out to make sure you get a show?
You'd want to plan, if you're going someplace, you want to plan 4 or 5 nights to be there, at least, if not a week or longer, to be, guaranteed. There's no guarantees, but to be more assured of getting a clear nights, and B, some active aurora. Now, when you go to a place underneath the usual location of the auroral oval, a KP 1 or 2 aurora is, like, as most of these were, is putting on a good show for you. But nevertheless, you'd like to have something even more dramatic, and you may not get that during the time that you're there, KP 3 or 4, and something that's even brighter and more colorful. You may or may not get that. But you want to go for several nights to one of these locations, and you might as well, if you're going all that way, to be better assured of getting everything coming together. Clear skies and solar activity and auroral activity as well. So most of these tours typically are several nights.
Now, Alan, we have one particularly enthusiastic RASC member and watcher who is wondering where she can go and see your tours in particular. Do you post about your tours on your website? I
do, but usually it's through I'm not a tour organizer. I'm an enrichment instructor. So I'm not organizing and putting on the tours. I don't want to get into the travel agency business. So if you go to the churchillscience.ca, go to their website, they don't have the tours up yet for next Aurora season advertised, because it's still a bit iffy what's going to be able to be offered in northern communities. So churchillscience.ca is a Northern Studies website, and that's where you can go to find out about the tourist offerings that they have for the polar bear season in the autumn and Aurora in the winter time, for example. Ron and I were doing Norway tours for a travel organization called Road Scholar, who kind of used to be to seniors, active seniors traveling, but it's really open to everybody. They're a US-based company, but they have tours literally around the world, or did until literally last year at this time when everything got shut down. And so we again are just hired by them to be enrichment instructors, but any bookings that you wanted for their groups were going through Road Scholar, .org, whatever their site is. And I looked the other day, and I didn't see anything advertised for them, because again, it's just all up in the air as to when they're going to next be able to offer things like Aurora cruises in Norway.
But of course, there's almost no COVID in New Zealand right now. So
seeing the Aurora australis from New Zealand that's risky, and as you said, it's people who are living there who get a chance to see it. But to go there and hope to see the Aurora australis on demand, you'd be very lucky, because they're far enough away from where the Aurora Oval is located in Tasmania and the South Island of New Zealand, kind of the two hotspots for the Aurora australis. They're far enough away. You need a KP 5 or 6 at least. And even then they might be seeing and be excited about a glow along the horizon. And I'm seeing that from my backyard in Alberta, and I'm going to bed. And so, although they can get good displays, but we are so fortunate in the Northern Hemisphere, and particularly in Canada, because that oval is tipped towards us on the night side in Canada, because the North Geomagnetic Pole is in northern Canada. So that oval dips down far, as far south as it does over us in Canada. Siberia on the other side, they can get auroras, but you have to go way to the north. I mean, in Norway, we have to go above the Arctic Circle to latitude of 68, 70 degrees, Tromsø, places like that, to get as good a chance of seeing the aurora as we can here in Canada at, say, Churchill at latitude 58, or Yellowknife at latitude 62. That aurora comes down farther south in this side of the world, North America, than it does on the other side of the world in Europe. So we can get good displays in Western Canada with a KP 3 or 4 or 5 that they're not seeing down south in the Southern Hemisphere at all, or very little, because they're not close. They're not close.
Go ahead.
Go ahead.
I was just going to say, we should also mention that the sun's activity level waxes and wanes on about an 11-year cycle, and we've just finished the minimum. So we're just barely started the ramping up of the more active sun right now. So the next 4 or 5 years could be really good for aurora, everywhere, especially in Canada.
Yes, it's picking up in activity, and the predictions of how active it's going to get at the next peak, which is 2024, 2025, vary from literally that's going to be a very low maximum to it's going to be a great maximum. The various groups that are making predictions based on their modeling of what the interior of the sun does are quite varied, and so nature will prove who's right. So it is ramping up, and that improves our chances of seeing great displays if we have a more active solar maximum over the next 3 or 4 years. Seeing great displays further south where most of us live. And that's where you want to look out for that auroral oval getting red on the diagrams and the KP going up to 5 or 6. And that could happen more often now at the next maximum, if it's an active one, that it would have at a very weak maximum.
So I see on this particular page, it's a great place to look at some of the different types of aurora that show up.
Sure.
We've talked a lot about the curtain type and the arcs, but maybe we could talk a little bit about the pillars here, these rays.
Yeah, if you want to go into the Alberta group there, Chris, I think that might show you some examples of different
Yeah,
kinds
look at those.
of aurora. Let's say, wait till it loads up. Usually there's kind of a, well, like on the very left there, top left, March 13th, 2021. No, sorry, go back up.
We have a little bit of lag in the screen time for
Yeah, there's a little lag. Usually, as you can see in some of these pictures, it often appears as just kind of diffuse arc across the north. As we can see here, like Aurora arc panorama, March 13th. So that was only, a couple of weeks ago. And that's often what we get in Western Canada, is just an arc across the north with maybe a little bit of structure in it. And that's the kind of thing that they're just getting thrilled about in Tasmania and New Zealand. And it's kind of par for the course here. But when there's a greater influx of particles coming in from the Earth's magnetic tail, that auroral arc, and you're seeing that oval stretching across the horizon. You're seeing that oval depicted across the horizon. That oval can now take on structure and start to get bands and rays and streaks and motion start to happen. The aurora starts to dance as a substorm begins to happen and the aurora gets more active. So if you scroll down a little bit, we can probably see some other examples of auroras. And then what can happen as well is after a very bright substorm where it's been really active and it settles down in terms of the traditional rays moving across and dancing across, is that you can get now kind of patchiness where whole bits of the sky are just flashing off and on and off and on. And that's pretty typical of kind of a post-substorm display, where it's just very pulsating. It doesn't have a lot of structure. It's just patches of stuff going off and on over the whole sky. And I've often seen that as well, following a bright display. It goes into that kind of pulsating mode.
So it's just sort of using up the leftover energy in the blast, and
well, it's a different process than the traditional raining down of particles from the magnetic tail. The pulsating, as I understand it, is made of particles that are actually bouncing back and forth. They're trapped in the Van Allen belts and they're bouncing back and forth. And this is happening all the time, but after a big substorm, they've been given enough energy, they actually come down to the atmosphere, and then they bounce back to the south and back to the north, and literally in a few seconds, and they're just turning off and on bits of the atmosphere. It's pretty amazing and really hard to kind of capture on a camera because it's happening so quickly. And then the other unusual type of aurora that no doubt people have heard about is Steve.
Yes.
And I have a gallery of Steve shots. Yeah, if you go back to the main page, and then there's a whole gallery of Steve shots.
We've had maybe 15 people being like, talk about Steve.
Okay, well, they're down there. There we are.
Yeah, so Steve is the strong thermal emission velocity enhancement.
Yes, that's a back acronym, as it's called. There's some shots of Steve from 2 weeks ago over my house. And that's right. It was, there's a whole story about how Steve got his name. And if you go on to TED, the TED Talks, Eric Donovan, who was instrumental in leading the research on Steve, has a TED Talk about it, how I met Steve. And he tells the story of how they identified this. It's been seen for decades. There's historical records going back, centuries, decades, about this unusual arc across the sky. And in southern BC, for example, they called it the Okanagan Arc, Okanagan Arch, where there's just this unusual band of light that doesn't seem to be doing too much to the eye. But you put your camera on it and it's got the pink and green color. And it's always south of the main auroral band, auroral oval. And it happens after there's a bright substorm to the north and it subsides. And then you might think, okay, the show is over. No, stick around. Because that's when Steve can appear as this thin line of light. And then he develops from east and then forms across the sky, goes all the way to the west. And to the cameras, he has this definitely pink, which is, we think, nitrogen, but up very high. Through doing parallax measurements of Steve pictures taken by amateur astronomers, some of mine included, where they've taken the same shots at the same time from different locations. They've been able to analyze where Steve is, and he's up 250, 300 kilometers, up really very high. It's not down at the edge of the auroral curtain, the bottom edge. It's up very, very high. But he has a vertical structure as well, with sometimes kind of green fingers forming along the bottom of the pink Steve arc. And the story about how Steve was, there you see one, there you see, there's a classic Steve formation there. And the story of how Steve was kind of identified was back in 2016, I think it was. Some Aurora researchers were getting together at the University of Calgary for a conference or seminar or some planning session, including researchers from the Goddard Space Flight Center. And after their conference or whatever, the word kind of went out to the Alberta Aurora Chasers Facebook group at the time that, hey, some of us are getting together for beers at a pub next to the university, kind of a watering hole next to the University of Calgary. You're free to join us. And I remember the note going out, and I just didn't have a chance to drive into town to join them. Darn, because that's when Steve was born. One of the local photographers, Neil Zeller, at the pub, sort of brings out his iPhone and says, "Oh, I took pictures. I have pictures here of a proton arc," which is what people were calling it at the time, because we were seeing these kind of strange bands. And Eric said, "No, it's not a proton arc." No, you didn't. So yeah, it is. There is a proton. Said, "No, that's not the proton aurora. All the auroras that we see and photograph are made by electrons. Protons can cause an aurora glow, but it's a very diffuse. It's a different kind of process, very diffuse. It doesn't form a thin arc. These are not proton arcs. It's a misnomer." And so, but then Eric said, "Yeah, okay, it's not a proton arc, but what is it?" And clearly it was something odd. And then we had to get a name to it because proton arc was wrong, just outright wrong. And so Chris Ratzlaff, one of the main administrator for the Alberta Aurora Chasers Facebook group, suggested the name Steve from a character in a cartoon movie, animated movie called Over the Hedge, where the characters are afraid of this thing that they don't know what it is on the other side of the hedge. So let's just call it Steve. We don't know what it is, but it's a more friendly name. And the name stuck, just Steve. And then Eric came up with the back acronym to say Strong Thermal Emission Velocity Enhancement. And because what it is, it's not caused by electrons raining down along those field lines, which is a normal aurora process. It's caused by stuff flowing horizontally, east to west across the continent, and heating up the atmosphere, very hot to incandescence. Except the green fingers do seem to be kind of stuff precipitating downward. And so it's a different process. It's related to aurora, but it's not a traditional aurora.
I read it was plasma.
It's very hot plasma. It is something unusual, and it only lasts no more than an hour, maybe half an hour. And this is a classic shot here, because there's the aurora to the north, the traditional aurora to the north as a glow, and it's subsided. And then Steve appears, very pink, usually to the camera, and with the little green fingers hanging down as well. And they move, slowly ripple from east to west. So it's material flowing from east to west, coming from someplace and going to someplace. I'm not quite sure yet. It's an area of very active research where amateur astronomers are very much playing a key role in supplying the data. Not only satellites, obviously in orbit and things like that, but we are supplying images like this are being used to triangulate and fix the position of Steve. I have my name on a paper coming out as contributor because I added photographs to this paper coming out in the American Geophysical Union journal about Steve and its relation to another kind of phenomena called SAR, subauroral red arcs, which we're known about for decades. And what's the relationship between those and Steve's? That's being studied. So it's a fascinating story of amateur professional collaboration and research.
And relatively recent, right?
Yes. Well, officially, in terms of being Chris and Steve, since 2016.
Wow.
Even though people have been seeing these things for years, they weren't really identified as something worthy of study and a different process than a normal aurora until 5 years ago.
That's crazy. On that note, Janine had a question from earlier. We've heard about Steve and the progression of research about Steve. In general, how has our understanding of how aurora even happen changed over time? Because she was saying that when she was younger, she doesn't remember us as a collective human entity knowing this stuff.
The aurora knowledge has improved tremendously in the last few years because, as Chris was pointing out, we have all these satellites monitoring not only the sun and its activity and its connection. We can see this material through a satellite like stereo flowing from the sun to the earth. But then we have satellites in orbit around the earth and in the magnetic tail to monitor what's going on. So all these numbers about KP and BZ and all that, that's coming from these satellites. We didn't have that 20 years ago. So we can monitor it much more easily than we could not so long ago. But the basic process of electrons raining down and causing aurora has kind of been known about since the turn of the last century. Norwegian physicist Kristen Birkeland first kind of came up with that model and even built little physical analog models of the earth, a little magnetized ball like called a Torella, where he put it in a vacuum chamber and then put a magnetic field inside it and aimed beams of electrons at it and created little artificial auroras in the lab. So he kind of come up with the basic idea a century ago, but it's only been in the last few years where the data has come in to support that. It wasn't until, for example, I think it was the 1960s from the Churchill rocket range that they got data from firing rockets up into the aurora from Churchill. Canadian scientists were part of that research, that they identified the electrons, that it was indeed electrons. That was theorized, but that gave them the actual data because you got to go up there. And the rockets sending rockets up is really the only way to do it, because the aurora is happening where satellites can't really fly. It's down in the atmosphere, but it's too high for balloons and things to get. So rockets, the only way you can kind of sample the actual aurora, where it's happening, when it's happening. And so it wasn't until the 1960s that they actually had data to say, yes, it is electrons. And
I guess they had rockets standing by that they could launch when they needed them, as opposed to something else that takes more time to plan and get ready.
What they did in Churchill and what they still do in Poker Flats, Alaska, and then Andoya rocket range in Norway, and there's another rocket range in Svalbard, where they put the rockets together in the experiments, and they put them, have them in warm huts all ready to go. And literally, when there's aurora active and the conditions are right, the doors open, they fire up the rockets, and it's liquid fuel or whatever however they do it. And then literally with no more than an hour or two kind of prep or planning, away they go. I mean, they might have the plan that they're going to do this experiment this month, but they have to wait for the right night to come along. And so that's how they do it. And the rocket ranges that are still left, but no longer in Churchill.
So is it okay, Chris, did you have a plan?
I was just going to say we could start talking about how to take photographs, but if you've got questions, sure. I
have one last question and a video to go along with it, so I'm going to steal your screen sharing if that's okay.
Go ahead.
So someone asked, I'm just going to play this in the background while I ask this question. Of course, the aurora can be seen from the ISS. Someone asked if you know if Steve has ever been seen from the ISS before.
No, not that I'm aware of. And in fact, I have not yet seen, even though I've asked and they've looked, people who look after some of the unmanned satellite data, weather satellite data that looks down, and you may see some of these pictures of the aurora from space over North America. In fact, they're often posted the very next day on Twitter of the last night's aurora. And there we are. We're just, is that flying over Canada there? And even they have not, in these satellites, have not seen Steve because he's so short-lived. And there just isn't a passage of a satellite or the space station over it when Steve is happening.
Right.
And so there was a couple of years ago when there was a big Steve outbreak, and I was, again, through Twitter, I was talking to some of the folks at the University of Wisconsin who post a lot of these satellite images from the unmanned meteorological satellites. And I said, gosh, maybe have you got an image from this hour, this interval? And they thought they had. It was a very straight line across their pictures. And then they realized, oh, that's just an artifact from the way they stitched the pictures together. It wasn't Steve.
Oh, yeah.
So no, but satellites have flown through Steve. And that's one of the key bits of data that Eric and other researchers used to identify what Steve was. Satellites not with cameras on them, magnetometers and other detectors. A satellite's called Swarm, in fact, that the University of Calgary have an instrument on, and it's a European Space Agency satellite fleet of satellites. They've flown through Steve and taken those measurements, but we don't have pictures of Steve from space. There are automated cameras that snap pictures of Steve from the ground, but it's still the amateur pictures that are still the main sources of data for the researchers doing work on Steve.
Speaking of satellites, don't forget that we get Aurora on Jupiter and Saturn. We've actually been able to take photographs. These are not optical. These are composite between optical and, say, ultraviolet wavelengths superimposed in order to show you where the aurora ovals are appearing on the planets. But yeah, it's any planet that has an intense magnetic field would interact with the interplanetary magnetic field from the sun and generate auroras. Of course, Mars hasn't got one, but the others do.
Mars has some patchy auroras. Yeah. The Maven spacecraft, I think it is, that's there orbiting, studying the atmosphere, has detected them as very low level patchy auroras because it's only got a patchy magnetic field. The difference between the Earth's auroras and all these other planets' auroras is that you wouldn't see those auroras if you were in orbit around them because they're not visible in the green, as we were talking. They're not oxygen.
There's no oxygen.
There's no oxygen there. And so it's hydrogen glowing or other elements glowing, or Mars, it's carbon dioxide. And they glow typically infrared or ultraviolet. And so it's taken special cameras to show those auroras on other planets. And from the Juno spacecraft in orbit around Jupiter, that one of the things is that it flies over the poles and looks down on the Jovian auroras. Fabulous. But only Earth has the green auroras because only we have oxygen. And so I in my lectures, I always say, if you want to find a planet somewhere else in the galaxy that has life or signs of life, look for green auroras, because A, that tells you that the planet's got a magnetic field, and B, it tells you it has oxygen, and that oxygen is glowing. Now, oxygen can come from other mechanisms, but our oxygen came from life. Microbes put it there.
It's a piece of the puzzle. It's a clue, right?
3 billion years ago. So we have auroras because we have life and we have magnetic fields, which are necessary for life to protect us from the solar onslaught. Mars doesn't have that, and so its atmosphere has been blown away by the solar wind.
So let's get into how you could get started taking photos of aurora.
Well, it's easy in some respects, especially, it's the groups that I teach. I almost say, if you've got an iPhone 11 or 12 or a late model Android, Google phone, whatever it is, it's actually the easiest. You just kind of hold it up and take a picture, put it steady, hold it steady on something, and let its automatic thing do it. It's night modes. The more modern phone cameras can do a marvelous job. And it's almost easiest because it is so automatic. You can't do a whole lot. It'll take an exposure of several seconds, and you'll get something. It won't be fabulous, but you'll get something. But you know, to get any shots like I show here, you're using a DSLR camera or mirrorless camera with an interchangeable lens and a nice fast lens, ideally f2.8, something like that. But you can get good shots with a slower lens, a kit zoom lens. But generally, you want a wide angle lens, 24 millimeter. Some of these are like 15 millimeter wide angle lens on a tripod, f2.8. ISO 800 to 3200. I can't tell you exact settings because it can change by the minute as the aurora brightens.
So if you suspect if you think you might be seeing a faint glow on the northern horizon, let's say I'm up at Georgian Bay in north of Toronto. I've been cases where I've thought I've seen it. Sort of what's my best exposure? First exposure time, 20 seconds.
Yeah, if you've just got a faint kind of diffuse glow along the horizon that you're just kind of thinking, that may be aurora, then yeah, 20 or 30 seconds, f2.8, f2 if you can go that wide, at ISO 1600, 3200. That'd be kind of your faint aurora sort of exposures. And you'll get something and it'll show up green where you won't see that when it's that faint to the eye. But once it gets bright, as we see in some of these shots, I'll be using exposures of only 1 or 2 seconds. Still maybe a high ISO, perhaps, to get the shutter speed as short as possible, to freeze the rapid motions in a still picture, or to make a rapid time lapse of it. And so, but if the aurora gets quite bright, normally you want to use maybe a little lower ISO, less noise, 800 or something like that, and still the exposure might be 5 or 6 seconds. The key thing, however, is the faster lens. That's really key. Having a lens that can be f2 or f2.8. The kit zooms are often like 5.6 or something, and it's tough. Really bright aurora, you can do it, but it's tough. You're fighting the lens for auroras or Milky Way shots. The faster lens and a wide lens, like a 14 millimeter to 24 millimeter, as fast as you can afford to buy, is what you want for aurora, especially if you're going someplace for a once in a lifetime bucket list trip. You buy the lens. These are all like the top row there is like a 15 millimeter fisheye. Full frame fisheye lens. When the aurora is going, you don't have a lens wide enough to get it all in. It's where do you aim?
So to get the Milky Way, is that something that just as a byproduct, or is that some extra effort to get the Milky Way?
Oh yeah, it's a byproduct. If you see the Milky Way in any of these shots, like up there, that's a byproduct, because the same kind of exposures, 20, 30 seconds, 2.8 ISO, 1600, 3200. That's what you need for the Milky Way as well. On a dark night, moonless night, and in a location away from city lights. So these auroras that you see on the top there, those are all pretty faint in some respects.
Yeah, I mean, in most of these, you can't even see stars once the aurora kicks up. Now, the ones you got with star trails, I guess that's a case where
if I've got star trails like we saw. Oh, there's a nice pink one there with the pink curtains down on the right there. But if you see star trails, I may have stacked a bunch of shots, like we saw in a few shots where you saw the stars swirling around. There, I'm stacking a bunch of shots. The typical technique for star trails as well. Now here you can see some really vivid reds and pinks in a Churchill display, which your eye probably wasn't seeing, but the camera picks it up very, very easily in this case.
When we're looking at these, is it safe to assume that if the structure is blurrier, usually the exposure was longer, and if the structure is crisper, then the short exposure was shorter? Yes.
Yeah. Any exposure over a second or two is going to blur the motion if it's moving very rapidly. Sometimes they can be slow, but when it's active and bright and moving rapidly, any exposure longer than a fraction of a second is going to blur the movement of the aurora. That's why people now, and I do as well, take movies. The cameras, some cameras are good enough. You can just take movies, sort of 30 frames a second, 24 frames a second, very high ISO, might be 51,000. But, you know, modern cameras like some of the Sony Alphas can do that, and produce a pretty good, and then in that case, the camera is recording more or less what your eye is seeing, the motion and the colors and the intensity. Because it's taking frames rapidly enough, more like your eye is doing. It's, you know, at 24 frames a second, something like that.
That's amazing.
So it can be done. And that's only in the last 5 years that those cameras have been good enough to, and affordable. They're not cheap, but they're not tens of thousands of dollars or 100,000 as they used to be. With some very specialized low light cameras. You can just walk into a camera store and buy a camera that'll take real-time movies of the Northern Lights.
Wow. And are you post-processing these very much, these photos?
All of them. Yeah, you're definitely bringing up the contrast and trying to accentuate the colors. They're all processed in Adobe Camera Raw typically, or Lightroom. You can use Lightroom as well, and also to enhance the dynamic range, or bring down the dynamic range. The Aurora is so bright in places, recover some of the detail in the bright spots and bring up the shadow details, things like that.
So if your camera records in RAW, you want to do RAW images if you can.
That too.
Oh, absolutely. That's true of any astrophoto. If it records in RAW, shoot RAW, and then do the post-processing in RAW. And it's really pretty easy and quick to do in something like Lightroom, or there's umpteen other RAW developers that will do a good job. Because what comes out of the camera RAW is purposely quite flat. It's meant to be kind of flat and neutral, and then you apply saturation and color and enhancements and whatever as you like.
And I'll jump in here just to say that almost every photo of anything to do with space has been post-processed. Like I can't think of a time when you would post something that hasn't been, when you could apply enhancements to it. So
yes, people tend to say, oh, you faked it or something, No, we're not doing that. We're not sticking stuff into the image that wasn't in the scene, things like that. And even if you shoot JPEGs in your camera, so that, I'm not going to process RAW. I'm going to just have what the camera gives me. Your camera is doing the processing in that case. The camera when it does JPEGs is applying contrast and color, and you can set various presets for those as well in your camera with the better cameras. And so that JPEG has been processed. It's not neutral, it's not RAW. And so there's processing happening with this. Oh, here was a comet last summer with, again, this low level aurora in Dinosaur Park, just a glow coloring the horizon. But there was a beautiful comet Neowise from last summer.
That's fantastic.
Now, I've heard some astronomers occasionally complain about Aurora, specifically deep sky astronomers and photographers, because the Aurora are actually light pollution for them.
Right.
Yes, when I lived in Edmonton for many years, and it may still be the case there. Well, auroras have become more popular and less viewed as a nuisance. But when I lived in Edmonton, we wanted to do deep sky astronomy, and that darn aurora would come up and wipe out the sky and prevent us from completing our message list or whatever. Nowadays, we kind of embrace the aurora a little bit more, I think, especially with the cameras being so good now, we can capture them. Back in the film days, it was a lot tougher. So yes, it can be a nuisance, but I think the rule now is people tend to embrace the aurora and, literally sort of chase after it and want to see the aurora and are desperate to see the aurora. Where to go,
That's right.
when do I go?
I'm not jaded. I'll take it.
On that note, there's one question from Joanne, and I'm going to put a little bit of a spin on it, Joanne. I hope you don't mind. Which was, would it be better to take a cruise in Norway or go up north in Canada? And I'm going to add in, what would you do? What is your go-to favorite?
Well, I do.
I was going to ask that too.
No, I think. I mean, Norway is wonderful. It's a great country, and the scenery is amazing. So if that's a place you want to go to anyway, then go in like February, March, or October, November. And what Ron and I do are Aurora groups, Atenta Aurora groups that are on the Hertegruten ferry service up and down the coast from Bergen to Kirkenes. And I'm not sure in the future what the status of that service is going to be, because the schedule was changing anyway with Hertegruten. But that's a wonderful trip. It's actually just a port stop all the way along, ferry service. But it's a great way to see Norway and see the Northern Lights. Once you get above the Arctic Circle, you're in the auroral zone. And so it's a wonderful trip to take. Even if you don't see the Northern Lights, it's wonderful. But, you know, for us in Canada, if you're in Canada, it's fairly easy to get into the auroral oval. Churchill is easy to get to from Winnipeg. It's expensive to get to. I just looked on Calm Air's flight scheduled the other day, and the prices have gone up because the flights had to be cut back because the travel, you know, the demand is so low, the prices have gone up. So it's expensive at the moment to get to Churchill, and always is. But Yellowknife is more accessible, and I haven't looked into airfares, but there's flights several times a day from Edmonton and Calgary and Vancouver up to Yellowknife, and I like going there in early September because it's not in the middle of winter. Prime aurora season is also February, March in Yellowknife, but oh boy, you know, it's minus 20, minus 30. We know that weather in Canada, but and so that makes it more challenging, especially if you're on your own going out there and trying to observe the aurora in the middle of winter. Early September is great, or late August, whatever, in Yellowknife. It doesn't get dark till late, but it still gets dark enough, and it's not cold, bitterly cold. And but later on in the fall in Yellowknife, I'm told from folks who live up there, RASC folks who live up there, that, you know, after mid-September, certainly by into October, the clouds are coming in a lot because it's right on the shore of a big lake that's freezing up. And so the chance of the clear skies become less as you get more into the autumn. But early September is kind of ideal.
And do some of these tours outfit you with warm clothing, or do you need to have all that?
Oh, yes. Yellowknife in September, you don't need that. Any Canadian should be well prepared. But I don't know if you're going as part of a tour group in middle of winter, whether they will outfit you. You'd have to check on Norway. You don't need because even in the middle of winter, it's not bitterly cold, not on the coast with the Gulf Stream. But Churchill, yes, they do. They say you should bring this and that and the other. And if you get there and you find it's not sufficient, you can rent some nice Canada Goose parkas, you know, great big parkas.
And boots. Good boots.
And boots, yes, absolutely, which is not something it's easy to carry and take with you. So tour groups like that will. In Yellowknife, I don't know. I go there on my own in Yellowknife, but not in the middle of winter. So I'm not with a group at all.
And if you don't have a good camera, I mean, I guess you can purchase photos, or maybe borrow or get photos from other people on the trip, or that kind of thing. I don't know.
Well, certainly on any groups that I'm leading or Ron and I are leading, we always have a photo sharing mechanism in some way where those without the cameras or good cameras can still have some photos as souvenirs taken by myself, Ron, or others on the trip. And when you're with a group like that, so usually that's the case. If you're with a group, there'll be some means of sharing what the group took or members of the group took, so you have your own personal souvenirs. But people like to be able to take their own picture, of course.
Sure, yeah. That's great.
And as you say, with most people at this point, depending on your phone, like I'm pretty sure I can adjust the exposure time on my phone to capture at something, even if it's not good.
Yes, and there are night capture apps on phones, but there are night modes now in the modern phones where it'll go into that automatically, or you can switch to it, and then maybe you can adjust the exposure, depends, and lengthen the exposure. The key thing with that is just holding it very, very steady. You might not have it on a tripod, but just put it on something and hold it very, very steady. Because I know with my iPhone 11, it will only go to the maximum of 30 seconds if it senses that it's being held steady. If it senses any motion, it limits the exposure to prevent blurriness. So use
your shutter delay and put it up on something.
Yeah. And so they're almost the easiest cameras. It's the people who arrive with the point and shoot travel cameras with the fixed lenses with zoom lenses and they're so auto this and auto that, and it's really hard to get into them to make a manual adjustments to those cameras, which inevitably you have to do. Those are actually the hardest cameras to use. It's the DSLRs at the high end and the phone cameras at the low end that are kind of the easiest to get results with.
Huh. And we're getting close to our time, but
Sure.
I did want to ask you, I don't know if you want to give up your industry secrets, but what do you use when you go out to look for or to predict aurora? What is your go-to? Do you have an app? Do you use a combination of the websites that we've shown?
Yes, I'll use those websites, spaceweather.com website, but the apps I use, let me just check my my iPad here and see what it is. Aurora Forecast. If you search for that, Aurora Forecast is an app that I have on my iPad, and I assume it's probably Android as well, where it'll show you that oval, the current status of the oval, and again called the ovation oval, and it will light up yellow and red. And when it's doing that, get out there. And then it has a forecast of what the KP is expected to be for the next few days or few nights. But again, that's always, you take that with a grain of salt. For example, right now it's showing that it could be a KP of 5 in early April, you know, in another week or two. And the other one I use is called Space Weather Live. App that I use, Space Weather Live.
Yeah, I had that one up for us. That was where I got the gallery of the sun. Here we go.
And again, it shows you the KP, current KP index and the auroral oval index.
And that
some of these.
That is both iOS and Android, by the way.
Oh, I'm going to assume so, but I don't know.
It is. Yeah, I just checked.
So here's the,
okay,
yeah, this is the Apple one. And then I had the Google one up a moment ago.
That's not the Aurora Forecast one. It's confusing because there's different apps called Aurora Forecast.
Okay.
That's not the one. And
Let's see.
on my home screen, it's called Aurora and then space FCST. I think that's the one. That's the one.
Yeah.
That's the one I use a fair amount. It's on my home screen. And yeah.
Perfect. Thank you.
Good. Well, we really appreciate you joining us today, Alan. I mean, you saved me a lot of work. Because of your knowledge base. It's fantastic. I really appreciate you coming on.
Well, my pleasure. Glad we could make this all work fine. And as you say, you've had this now because this is kind of prime aurora season. It is quiet for the next little while in terms of forecast activity, but from here on, I mean, especially in more southern Canada, even through as we get brighter nights, May and June, we can still get auroras. Not up in Yellowknife. You don't want to go up there in June unless you want to go for some other reasons, but you won't see aurora. But we are kind of prime aurora season right now. And then again in September, August and September, and into October as well, in terms of being close to the equinoxes. But from more southern part of Canada, we can get auroras anytime now for the next while. It's not, we don't need, even though I'm standing here with my parka on in the snow, we don't need cold weather to see the northern lights. Don't think that it has to be cold. That's still kind of a misconception that even some of the old timers say, oh, it's too cold or it's not cold enough to see the northern light. No, it can appear in the middle of summer.
That's great. Well, I guess people can follow you, Amazing Sky Guy. You're on social media. Once you're ready to resume your tours, or not your tours, but host, be the subject matter expert. People can be alerted and join on. Yeah, we don't have anything scheduled at the moment. We do have Aurora tours. Well, we have the weeks set aside and the days set aside. Tour dates set aside for Churchill for next February, March. What's going to happen? We don't know yet in terms of restrictions and access. Northern communities are being very, very cautious about letting in visitors.
Well, Well, we all have our fingers crossed, and something to, even if we can't actually do it, something to look forward to, which is really, really nice. Thank you so much, Alan, for sharing all of your knowledge on this. Your work is amazing, and I'm sure we have inspired many people to go out and hunt down those auroras. So,
very welcome. Thank you.
Alrighty, as Chris said, please follow Alan on social media. You can follow us too, but Alan's handle is Amazing Sky Guy on almost all platforms. The links will be up in the YouTube description after we finish up this presentation, so you can go back there if you need to look at any of the apps or anything that was presented. And one last plug, if that's okay with everybody, we have a new show starting on Thursday where we're going to be looking at the moon, which has nothing to do with Aurora at all, but we'll be going over RASC's Explore the Moon Observing Program, where you can earn a pin and certificate for seeing craters, mountains, valleys, etc. on the moon. So that will be Thursdays at noon until June. Wow, there's a lot of rhyming there. Thursdays at noon until June 17th. You can head over to rasc.ca/moon@noon if you would like to sign up, and we will see you in the next session, which I didn't prepare. Hey, Chris, what are we doing next time?
We're doing our April break, our March/April break program geared towards students, library patrons, things like that. Yeah, during the April break week, and I've got some cool things in mind. I mean, we're gonna learn to use a starfinder. We're gonna talk about Harry Potter characters in the sky and maybe tell some stories from star lore. Yeah, it'll be fun.
You don't have to be a library or at a library or supporting a library to come and join us. So
no, and you can be a grown-up too.
You can be a grown-up, yeah. So we'll see you in 2 weeks for those who are not joining us on Thursday. Thanks again, Alan and Chris, and I hope you all have a wonderful rest of your Tuesday.
Thanks, everybody. Keep looking up.